So, welcome. We are now going to discuss about application of Taylor polynomials. Again, as we said, Taylor polynomials are implemented as circuits in your computer devices so that you're able to compute uh, values of certain functions, like say trigonometric functions, like sine, x, so on and so forth. So reminder, if a function f has a power series representation at x equals to a, which is given by n equals to 0 to infinity fn a x minus a to the power n, this representation is called the Taylor series of function at a. The second reminder is the following, which is a Taylor's inequality. So Taylor's inequality tells you, suppose you took your function f of x and you approximated this function by a Taylor polynomial of degree n. Then of course you will have an error or remainder term. There's a bound on this remainder. The remainder term, after you approximate it as Rn with Tn, the remainder term is bounded by m upon n plus 1 factorial x minus a to the power n plus 1 for all x minus a less than or equal to d, where what is your m? Your m is a bound, it's the bound on fn plus 1th derivative of x on all x such that x minus a less than d. So the idea is of writing this thing here is you are, of course, doing this approximation. You have a and you're doing this approximation all the way from here to here, which is a minus d to a plus d. And the endpoints included, right? That's what this means. So, and if you have a equals to 0, you get a Maclaurin series. So let's work on an example. So approximate f of x to the power 2 by 3 by Taylor polynomial with degree 3 at a equals to 1. So let's look at this part here now. So we need to compute f. So we need to compute t3. So we'll be interested in n again when n is 0, 1, 2, 3. Because after all, a Taylor polynomial of degree 3 will look like what? T3 of x is f of a plus f prime of a divided by 1 factorial times x minus a plus f double prime of a divided by 2 factorial times x minus a square plus the third derivative of a by 3 factorial times x minus a cubed. This is what your Taylor polynomial of degree 3 is. Okay, so we need to compute the third derivative all the way until third derivative. So let's compute that. So we have f of x. So what is our f of x? So our f, so we need to compute fn of x, and then we'll compute fn at a, which is computing fn at 1, right? So we are computing fn at 1. So the first derivative, zeroth derivative of function is function itself. So this is going to be x to the power 2 by 3. And we have what? When you put 1, you get 1. Now, when you take the first derivative, you get 2 by 3 x to the power 2 by 3 minus 1, which is minus 1 by 3. And when you put 1, you get 2 by 3. Next, you take the second derivative. So this is going to be, again, I'm using power rule. So 1 by 3 times 2 by 3 is going to be minus 2 by 9 x to the power minus 1 by 3 minus 1. So it's going to be minus 4 by 3. And again, when I put 1, I get minus 2 by 9. Then third derivative is going to be, multiply this again. So it's going to be minus, so 8 over 27 x to the power minus 4 by 3 minus, so minus 7 by 3. And then when you put 1, what do you get? You get 8 by 27. So what is my T3 of x? Therefore, T3 of x is f of 1 or which is going to be 1 plus, now we have f. So first one would be 2 by 3 times x minus 1. Then the next term would be 2 by 9 times x minus 1 squared plus 8 by 27 times x minus 1 cube. So this is your approximation. And of course, we have to divide by appropriate factorials. So multiplied by 1 factorial, multiplied by 2 factorial, multiplied by 3 factorial. So this is your Taylor polynomial of degree 3. Now we have to use Taylor inequality. So B, so we know that Rn of x, so we need to find out Rn of x is Tn x minus f of x. Oh, sorry, my bad. F of x minus Tn of x. And we won't work out f of x. So we use the following. Rn of x is bounded by m divided by n plus 1 factorial times, so what is the formula, is x minus a to the power d, where what happens, where x minus, so in this case we have, this is 1, x minus 1 is less than equal to, x minus 1 is less than equal to d, and this has to be n plus 1. Okay, so let's find this out now. So first of all, what is m? M is, so if I rewrite this, this is going to be R3 of x is going to be less than equal to m times 4 factorial x minus 1 to the power 4 for x less than, x greater than 0.8 less than 1.2. So now if I want to write this in the following format, what shall I do? In that case, I will write down subtract 1. So I get x minus 1 is less than equal to minus 0.2 less than equal to 0.2. And this means x minus 1 is less than equal to 0.2. So this will go, this value will go here. Okay. But before we do that, we need to find out m. So let's find out m for once and for good. So let's find out m. So for that, notice what is f4 of x? What is the fourth derivative of this? So we need to find out m, which is, so what is f4 of x? Is again derivative from here, from this part, and that is going to be minus 7 is a 56. So 56 by 81 x to the power minus 10 by 3. So now what is a bound on? So we get what? We need bound on f4 of x, right? Because that is what our m is. Our m is bound on this guy. So let's look at this guy. So f4 of x is absolute value of that is equal to absolute value of 5 by 80 times 1 upon x to the power 10 by 3. And we are interested in one what? On 0.8 less than equal to x less than equal to 1.25. Now in this interval, what is the maximum value of this? Note that this function is a decreasing function. So the maximum value will be achieved at, so f4, this is a decreasing function because the denominator is getting bigger and bigger. So this is going to be less than equal to 56 by 81 multiplied by 1 by 0.8 to the power 10 by 3. So now plug everything back in this equation. So therefore, R3 of x is going to be bounded by, first of all, this is your m. So m, which is 56 divided by 81, 1 upon 0 0.8 to the power 10 by 3. This is your m divided by 1 by 4 factorial times x minus 1 to the power 4, and that is less than 0.2. So this is going to be 0.2 to the power 4. Okay, so this will become 0.2 to the power 4. So and that is the answer. Okay, so you simplify this, and this is what you get as an answer. All right. So this is how you use Taylor inequality to find out what will be the error in your computation. Now let's look at the following. Approximate the area between the curve y equals to sine x from minus pi to pi. Yeah. So first of all, what do you want to find out? You want to find out pi to pi of sine x over x dx. Not quite though, because, well, so you have minus pi to pi. So you want to find out area between the curve and x-axis. So you want to compute this integral, right? So want this integral to compute this integral. Yeah. So what the idea is, replace by Taylor series, or actually Taylor polynomial, not Taylor series. Yeah, we want a finite computation. So note that sine x over x looks like somewhat like this. So this is the area you are interested in, from minus pi to pi. So let's compute the Taylor polynomial. So what Taylor polynomial? We can basically work with n equals to 3. So let's compute the Taylor polynomial for this guy. So we have fn of x, and we have fn of 0. So where f of x is sine x over x. Yeah, so we'll, instead of writing the function, we are going to use the Taylor polynomial. So this can be alternative for, this method is an alternative method to Simpson's trapezoid, etc. rules. Yeah, which we have discussed earlier. So let's write down. So we have, if you take 0th, you'll get first derivative will be 0th derivative is the function itself. And then if you take the first derivative, you'll get x cos x minus sine x by x squared. And then you take the second derivative, it's going to be more complicated. You have 2, you have x squared minus 2 times sine x plus 2x, so plus 2x cos x by x cubed, right? So that is one way out. And then you have to compute fn of 0. However, instead of computing that, what if we write down the Taylor series directly? How would we do that? So sine x is, note that it's basically x minus x cubed by 3 factorial plus x5 by 5 factorial, and so on. So sine x by x will have 1 minus x squared by 3 factorial plus x4 by 5 factorial, and so on. So instead of computing that value at 0, yeah, why don't we basically work with, so let's work with t3 of x, which is going to be, so t2 of x. So t2 of x is going to be, in this case, we have t2 of x is going to be 1 minus x squared by 3 factorial. Yeah. So therefore, sine x, we have sine x by x, we are approximating it by t2 of x, which is 1 minus x squared by 3 factorial. So therefore, if you want to have this integral, sine x over x dx, this is same as integrating roughly, all right, minus pi to pi of minus 1 by x squared by 3 factorial dx. So let's compute this. So we get integral. Now, what kind of function is this? This inside is an even function. So you can write it as 2, 0 to pi, 1 minus x squared by 6 dx. And that is going to be 2 x minus x cubed by 3 times 6 is 3 6 are 18, 0 to pi. And then when you basically write it down, so you get 2 times pi minus pi cube by 18, and this is your basically the answer. Okay, so that's how it goes. So we have approximated it by t2. Now one may ask question, why did you approximate by t2? Why not t5? Well, you can do it with we can do it with t4 as well. The result would be more or less, it will get better. The approximation will get better.